Okay, so this mini lecture is going to recap vector components. So how do I find the horizontal and vertical component of a vector? So, for example, when we look at an object's velocity, it's possible that that velocity is occurring at an angle. So let's imagine that we have an object being thrown into the air or hit into the air at an angle of 30 degrees. And it's being thrown with a velocity of 5 meters per second. So here's our velocity vector. And we're going to need to determine various players of motion and maybe information about this particular motion, how far it travels, how high it gets. And in order for us to do that, and we will find in the next chapter that we're going to separate our motion into horizontal and vertical directions. To do that effectively, we need to remind ourselves how to get the components of a vector. So if I am shooting my ball at 5 meters per second at a 30-degree angle, another way to describe that is I am shooting it up and to the right at 30 degrees. So there is an up piece of this velocity, a velocity in the vertical direction, and there is an over piece of this velocity, a velocity in the horizontal direction. And so when we analyze the motion, we're going to separate those two directions. And so we want to make sure we understand how to get the horizontal and vertical velocities, the components. So this mini lecture is on those components. How do we get the components of a vector? And we have to remember our trigonometry. Remember, our trigonometry is abbreviated by the acronym SOHCAHTOA. And whatever story you heard in geometry class of the origins of SOHCAHTOA might be different across the country. But it helps us remember how to get the components of a vector. All right, so if I'm interested in the horizontal component, in this case, that is adjacent to my angle. It's right next to my angle. Cosine relates to that adjacent. We remember that the cosine of an angle is equal to the adjacent over the hypotenuse. If I want that adjacent value, I can multiply the hypotenuse by both sides. And in this case, my hypotenuse is 5 times the cosine of 30. So my horizontal component, my adjacent side, which is equal to the horizontal component in my example, is 5 times the cosine of 30, 4.3. And our components will contain the same units as our vector. Okay, vertically, well, that's opposite my angle, so my vertical component is the sine of the angle is equal to the opposite over the hypotenuse. So my hypotenuse, or my velocity, times the sine of my angle is going to give me, in this example, my y component of the velocity. So 5 times the sine of 30 will give me my velocity component. So 5 times the sine of 30 gives me 2.5 as my velocity component, meters per second. So that's how we go from a vector into its respective components. We want to make sure we're careful and that we're looking at the picture. So I'm going to erase this and do another example where the picture changes a little bit and it forces us to be careful about it. Okay, so this erased. What if I am throwing an object down and to the left at an angle of 30 degrees? So for ease of numbers, since I already have them calculated, we will do an example where I am throwing an object down and to the left. And I am going to say that that is with 30 degrees in that fashion. So here's my picture. the velocity is equal to 5 meters per second. Okay, so down and to the left. So I have a down component that's going to represent my vertical velocity, and I have a to the left component that's going to represent my horizontal velocity. There's a variety of different ways that we can do this. If we want to stick with SOHCAHTOA and let our mathematics out of our calculator give us exactly the right number, then we need to remember to take our angle with respect to the positive x-axis. On this example, we took the angle of 30 degrees. The positive x-axis is this axis here, if I draw a coordinate system on there. And so this 30 degrees is indeed with respect to the positive x-axis. Furthermore, we used a positive 30 degrees. A positive angle is an angle as we draw it from the x-axis in the counterclockwise direction. And that's how we've represented it. Or that's what the math we did, and that's a more visual representation of that. So, there's a couple ways for us to think about this problem. First, we could just use our 30 degrees. Now, if I calculate the same horizontal and vertical components with 30 degrees, I'll get the exact same answer I did in this problem. So, our horizontal velocity out of my calculator will be 4.3 meters per second, and my vertical velocity out of my calculator will be 2.5 meters per second. That's what the calculator will give me because I have not changed the math I put into it. But are these accurate? Is that the right representation of the components of this vector? No, they're not. What do we notice about this vector? First of all, the velocity horizontal is to the left, which tells me that should be negative. And so if I just use the angle as if it were not caring in the world where it was, then indeed I have to put in that negative value. I have to be attentive to the physical situation that I'm presented with, and that's okay, as long as we remember to do it. Vertical velocity, same thing. It's down. So it too needs to be represented as a negative. So in this example, we're only looking at the magnitude of these two components by using that 30-degree angle. And our physics understanding tells us that we have to put those negatives in. Okay, and I am totally comfortable with you doing it that way, and that's the way a lot of people are comfortable with doing it. However, if you like your calculator giving you exactly what it needs to give you, meaning what you put in is going to give you the output that you know is right, with those negatives in this case, then it's going to be very important that you reference your angle to the positive x-axis. Whether in these examples that positive x-axis is in our Cartesian coordinate system relative to the Earth horizontal, what we usually think of it, or as we move into forces and we rotate that axis. So what happens? Let's just look at that and see if it gives us what we want in terms of our positive x-axis. So here's the axis. If I take my angle with respect to the positive x, this becomes the angle I'm interested in. That angle is 180 plus 30 degrees, so 210 degrees. Now, SOHCAHTOA will work for us in absolute. All right, so reminding ourselves that the vertical component, horizontal component, is the cosine. So the cosine of my angle in this example is my opposite. Well, forget the opposite, is always the horizontal. If I use the angle relative to the positive x-axis, the cosine will always give me my horizontal component. So it will be my horizontal component over the hypotenuse. So to get that horizontal component, I will take the velocity times the cosine of the angle with respect to the positive x-axis. So 5 times the cosine of 210. So if I plug that value into my calculator, 5 times the cosine of 210, I get negative 4.3 meters per second, exactly what I should. If I do the same thing, if I always reference to the positive x-axis for the vertical component will always be given by the sine, using the sine. Oops. So my vertical component will be the hypotenuse, the velocity, times the sine of my angle. And if I plug in 100 or 210 degrees for 5 times the sine of 210, I get negative 2.5 meters per second. This now tells me my component velocities as they should be, as the physics represents. Either way is fine. You just have to make sure you're paying attention. Know the physical representation of the world so you know what you expect to get. If you choose to do interior angles to get your values, that's fine. Just you have to be explicit and put in the signs that are important for the physical quantity. If you always reference your angles relative to the positive x-axis, cosine is always going to give you the horizontal component, and sine will give you the vertical component in a Cartesian system that you define, whether it's Earth horizontal or at an angle. All right, I encourage you to try some angles in the other quadrants and make sure you understand when you need those negatives and positives. Good job.